Thank you. I guess you can hear me okay? I'm going to stand up today. I like to stand when I talk. So thank you for having me here today. It's an honor to be here, and it's been a wonderful experience so far. So thank you for coming. Again, my name is Darryl Butt. I'm the College of Mines and Earth Sciences at the University of Utah. How many people in here have been to the University of Utah? I know there's at least one. How many have been to Utah, the state of Utah? At least one? Good, okay. So it's a very beautiful state. What I'm going to do is I'm going to give you a little bit of an introduction to our university and to my college, and then I'm going to give a technical presentation. And the technical presentation, let's say, is the theme of the presentation is about how to construct a phase diagram. Okay, that's what we're going to work on today. So I always forget how to use my pointer, so bear with me. If I hit you in the eye with the laser, I apologize. So we are a comprehensive university. In other words, we're a university that has many, many colleges and many disciplines. We have 19 different colleges and schools. We have 100 academic departments. We have 35 interdisciplinary programs. And what that means is that we have programs where you get your degree not in one college, but in multiple colleges, usually 2 colleges. And then we have 7 medical divisions. Just like this university, we have a medical side of what we do, and we have sort of the other side of what we do. We're a technical university, a liberal arts university, but also a medical university. And this is Salt Lake City, the area, a portion of Salt Lake City. My house is right about here. That's where I live. And our buildings, we have 6 buildings that we occupy, our college. We primarily are in 2 buildings, but we occupy 6, and we're right around here in the center of the campus. And you can't see it in this picture, but the medical school is up on the hill. So we call them the upper campus, and we're the lower campus, is the way we describe it. So we're also a member of the Pac-12. It's called the Pacific 12. And what that means is that we collaborate with 11 other universities in athletics and also in academics. And so if any of you are really fast or you can lift a lot of weight, you can get a scholarship to our university to compete in athletics. And the schools that are part of the Pac-12 are the University of California, Berkeley, Arizona State University, University of Colorado, University of Oregon, University of Washington, Washington State University, Stanford University, UCLA, University of Arizona, there's us, University of Utah, Oregon State, and the University of Southern California. So all of these schools are our peers, in other words. So we are at the sort of the same level in some sense as these schools. Academically, we are somewhere in the middle. Athletically, sometimes we're at the top and sometimes we're at the bottom. But all of these schools work together to improve their academics as well as their athletics. And one of the reasons that I put this up here is to show you who our peer institutions are, but also to let you know that the University of Utah, in terms of the cost of education, is the second lowest of all of these schools. So we're fairly affordable compared to the other schools. University of Washington is the only school that's less expensive than us. My college is also comprised of 4 departments. We have a total of 18 different degrees in our college, and those 18 degrees reside in these 4 departments. We also house a seismograph station. So we monitor all the earthquakes from down in the south part of the state of Arizona, which is down near Mexico, all the way up and through Yellowstone National Park and up towards the border of Canada. So we monitor all the earthquakes along sort of the, I'll call it the western side of the Rocky Mountains, which is a very active region for earthquakes. The four departments that we have are atmospheric sciences, geology and geophysics, metallurgical engineering, and mining engineering. And the primary reason that we came here today to visit is because we're trying to develop collaborations with your university, primarily in metallurgy, mining, and geological engineering, geophysics, or geosciences. So each of these different departments has their own strengths, and I won't go into all the details. I'm going to show you a couple of examples of things that we do in a minute. But our atmospheric science department is considered one of the best programs in the world for mountain meteorology. So we help predict local climates, especially in mountainous regions, and that's their specialty. But they also monitor hurricanes, and they do weather reporting, and we're also experts in snow, as you can imagine. Our geology and geophysics department, and we also have a geological engineering department, I would say specializes in, let's call it paleoecology. So we study ancient humans, dinosaurs, things like that. We have one faculty member who discovers a new species of dinosaur every single year. In a few minutes, I'm going to show you a real dinosaur in action too, by the way. We also work on discovering ancient human remains. One of our faculty was involved in a team that discovered the oldest complete human skeleton in the world, which is 1.7 million years old, and that was discovered in Kenya. And if you've heard of Lucy, the skull Lucy, he also contributed to the kind of the dating and discovery of that skull. His work led in part to that. We do lots of other things, and I'll talk about some of the other things in a minute. Our metallurgy department is, Our metallurgy department is now the only standalone metallurgy department left in the United States. And we have a metallurgy department, and we have a material science and engineering department at the University of Utah. There are other universities that have both mining and metallurgy combined, or metallurgy that has been merged into material science and engineering, but we're the only one that has a pure metallurgy department left. It's a very, very strong department. In terms of research, it's one of the strongest departments at the university. And then we also have a very strong mining program, and the mining engineering program is really focused more on undergraduate education. I'm actually trying to change that right now, so there's more graduate education, but we're very focused on undergrads. So we are here in part because we're hoping to get undergraduate students to come to the University of Utah in the future, and also to get graduate students to come. We're trying to create some joint programs with your university, and hopefully that'll get started fairly soon, and you'll hear more about it from some of the folks here at Central South University. So this is some statistics on our college, and I won't spend a lot of time on this, but I do want you to understand our college is kind of unique. We get funding from the state of Utah. We also charge tuition, just like you do. But we also have what's called an endowment. We have a large endowment, or really a collection of endowments, about 54 million US dollars. And essentially that is held in a bank, and we collect the interest off of that. And one of the things we do with that interest is we create scholarship opportunities for our students. So we have this fund that we're able to pull money from so that we can fund our students, give money to our students so that they can afford to go to school. So we try to keep our costs very, very low, and we do that in part because of the donations that people have made to our college over the years. We also have many paid research opportunities. If you come to our campus at the University of Utah as a graduate student, we don't charge you to go to school, we pay you to go to school. So you don't pay tuition, and we typically will pay around 25,000 US dollars per year to go to school, to get your master's degree or your PhD degree. For the undergraduates, we also have paid research, excuse me, and the undergraduate students get paid around $12 an hour, and they're allowed to work up to 20 hours a week during the semester. And you work in the laboratory with a faculty member and other students. So as an undergraduate student, in addition to going to class, you can also do research, you can get publications, and by being part of a research community, what you'll find is your grades improve, your scores improve, because you stay on campus, you work there with the other students, you have a mentoring system, and but you also get paid to do that. So we try to make college at the University of Utah as affordable as possible, particularly in my college. And I think I'll skip to the next slide. Another thing I'd like to point out is we are what I call a college of the earth. And so we have, the last time I counted, we have at least research activities, collaboration, or academic activities going on in 65 different countries. That's every continent and every ocean. And these are just a few images of some of our students last year in different places. They went to Peru, we had students in Greenland, Japan, South Africa, Ecuador, and this is just a fraction of all the places that our students have gone over the years. And they get, some of these are just week-long experiences, some of them are maybe for a summer, in some cases they're exchange programs. So we like our students to have international experiences. These are some images of our students in action, I like to call it. Depending on your major, you'll get a lot of experience out in the field. As I said, Utah is a very, very beautiful state. So a lot of our students end up doing things like studying rocks out in the desert, in the canyons, studying caves, working in snow if you like snow, more snow. We also have some lakes nearby. We're called Salt Lake City. So there's some giant lakes, and we do research out on lakes. But our students actually do a lot of their work outside, and our classrooms are sometimes outside. This is just another image of one of our students in action. And I thought this would be just kind of fun to show you. So every month or so, we have an open house in our college. And we do this in the evenings, and people bring their families, and we have some food, we have a speaker or two, and we invite the community in. And this is one of my students right here, dressed as a dinosaur, and I thought you would enjoy this. It's kind of fun. I don't know if the sound will work, we'll find out. The sound's not working, but you get the idea. Anyway, you get the idea. So that's one of my students, and by the way, I gave him a $1,000 scholarship for doing that. So if you come to the University of Utah, if you're interested in dressing up like a dinosaur, we have opportunities for you. It's a fun place to be, is the point. So what I thought I would do is talk in general about some of the research areas and some of the academic areas where we have a lot of expertise. And I'm not focusing on any single department. I'm focusing on, we're trying to highlight, I should say, areas of expertise that cross the disciplines of our college. So all of our departments in some sense work in big data. And we have a lot of expertise, and we make a lot of use of satellite data, data from ships, sensors that are located all over the world. Because we're so data intensive, big data is very important, and therefore we do a lot of supercomputing work. If you like computational work, the University of Utah has a large high-performance computing center. A lot of universities in the US have stopped doing that, but we've retained our high-performance computing capability because it's so important to our university. So we have a really, really good high-performance computing center at the university that we make use of. And we also put our own sensors out in the field, And for example, we have seismograph stations, around 270 seismograph stations planted all over the Rocky Mountains. We use to collect data on earthquakes. And then because we collect so much data, it's really important for us to communicate with the public what our results are. And so one of the things that we do is report earthquakes. When there's an earthquake in our region of the United States, we are required, we're paid by the US government, we're required to report that earthquake within a matter of about 3 minutes if the earthquake is over a 3.5. So we report earthquakes to the public. So you guys have probably heard of Yellowstone National Park. We monitor all the earthquakes in Yellowstone. And last summer we had 3,000 earthquakes, over 3,000 earthquakes in Yellowstone. And we were constantly reporting those earthquakes to the public so that we keep people safe. So that's the kind of thing that we do. We also do a lot of work in development of sensors and also nanometer scale devices. So we do nanoscale device fabrication, and we also use sensors in various applications. Some of the things that we do, for example, are we use sensors and devices to purify water, to detect whether food is safe. We're developing sensors for detecting disease, for example, tuberculosis. We're working on a sensor now, if you breathe on it, it will tell you that you have tuberculosis. We also put sensors on mass transit systems so that we can monitor pollution all over our valley, just like a lot of places in China, and especially because of the mountain range that we're up against. Salt Lake City has pollution issues, and so we monitor the distribution of the pollution in the valley and try to use that to make decisions about how to control traffic, where you might want to live, for example. I live in this red area, which is high pollution, and people that are out here have cleaner air, for example. So you might choose to live out here rather than here, although it tends to be more expensive the more pollution there is for some reason. We also develop sensors for things like mining, ubiquitous sensors for mining, as well as or make use of ubiquitous sensors as well as implement sensing devices into mining operations. So a lot of our work is in sensor development and sensor applications. We're also world-renowned for our work in isotopes. So we use isotopes to date things and characterize things. We have a whole series of different types of instruments to measure isotope concentrations. And some of the things that you use isotopes for example, are paleoecology, for dating soil. So if you dig up a fossil, if you characterize the isotopes in the fossil, but also the minerals around it, you can date the fossil. We also use it, for example, for characterizing things that are not so old, like ivory. We have a program with Africa where we characterize the isotopes in ivory, and we're able to determine where that elephant came from, and that allows us to identify what region of Africa the elephant might have been poached from. And so we help the African government stop poaching of elephants using isotopes. This is actually a picture of my brother doing what I call fish juggling, which is a very difficult thing to do. Have you ever tried fish juggling? No? Okay. Whoops. Yeah, I'm just joking. I don't know how he got that picture, but he caught this fish and it flew up in the air, so I kind of threw it in here. But one of the things we do is we take the cartilage associated with the ear of the fish, of a salmon, and then we characterize the strontium isotopes. And by looking at those strontium isotope ratios, we can determine where that fish came from. And so by looking at the fish that are caught on ships, say in Alaska or the Pacific Ocean, the northwest United States, we can determine where the fish came from, and we can kind of understand how fish populations are changing, how fish populations are being affected by global climate change, and that sort of thing. And another thing I'd like to just point out is we have what's called an isocant at the University of Utah, and we would love to get some students from here to come and participate in ISOCamp. It's a very, very competitive camp. You have to apply and you have to be accepted. But if you're a very, very good student and you're interested in doing research in this area, this camp is an incredible experience. So students come to Utah in the summer, and our camp is starting in about a week or two, and they get all kinds of research experience with our equipment. They'll get a project, and for example, you might study water chemistry in the Wasatch Mountains, or maybe you study dirt from a fossil. But all the students have a project, and at the end, they present their work, and in some cases, the students end up in just a short period of time publishing papers in peer-reviewed journals, like Nature and Science. And the students that graduate from this program go back to their universities, and it turns out they're very, very successful because of this experience. The two individuals that run the camp, Terry Serling and Jim Ilringer, are world experts in this area. They're both members of the National Academy of Science, and the experience that the students get is like none other. And in fact, some of the graduates of this program, there have been about 800 graduates. Many of them have gone on to become National Academy members, professors at universities, and so it's a really good training ground for anyone who's interested in isotopes. Another area where we have a lot of expertise is what I call inverse theory, and that sounds pretty boring, but let's describe it this way. So if you have a roll, a muffin, and inside that muffin you have nuts and raisins and pores and I don't know, ants or hairs, and I asked you to tell me the distribution of everything in that muffin, the dough, the pores, the nuts, the raisins, and I want you to do it in such a way that you tell me spatially where everything is, you tell me what the density is, maybe I tell you I want to know what the chemistry is or the crystal structure, and I want you to create a model of that in 3 dimensions. I want you to be able to separate all the different phases, so to speak, and rotate it in 3 dimensions. So that's kind of what we do. And what I want you to do is, I want you to do that without ever cutting the muffin open. Only use tools from the outside. So things like sound waves and electric currents and other things can be used in order to characterize what's inside of a material without causing damage. And so these are just a few images of the kinds of things that we do. We do this sort of thing on the scale of the Earth to very, very small scales. This is actually some of my work, which is similar to Dr. Jan Miller's work. Some of you might know that name, Jan Miller, who's been here a few times. This specimen is about 100 nanometers by 100 nanometers. So it's about 1/100th the diameter of a human hair. And so we use different tomography techniques to go in and probe this material and then split it into multiple components. So we do things, we look inside materials at scales from the size of the human hair to the size of the entire planet and everything in between. Another area that is very important to our college is what I call E squared R5. In other words, energy, environment, recycling, reuse, recovery, remanufacturing, and resilience or sustainability. So trying to make the most out of the materials that we have and minimizing waste. This is something we're not very good at, frankly, in the United States, and we need to get better at it. So we have a very, very large center. It's an international center. I shouldn't say internet. It's a national center that involves 25 universities, I think 23 companies, and 7 national labs. And that's something that many of our students are participating in now. They're starting to participate in. Another area that I don't have to talk to you about because you know a lot about it is the importance of materials from the earth in developing green technology. So nuclear energy, solar energy, wind energy, electric vehicles, batteries, fuel cells, all of these materials come from the earth, come from mining. And if you look at the materials that we need over the next just 15 years for electric vehicles, there's all kinds of new exotic materials that we're going to need to get from the earth in order to satisfy that demand. So we worked a lot on trying to figure out ways to get these materials out of the earth in our part of the world. So what I'm going to do now is I'm going to switch. So that was about the University of Utah and our college, and now I'm going to talk a little bit about some of my own research. And so this is a technical presentation. Do you guys need to stretch? Everybody okay? You keep going? Okay. So what I'm going to do is talk about perovskites and phases that are similar to perovskites but not quite perovskites. So I call them sister structures. A lot of people aren't aware, perovskites are incredibly common materials on Earth. They tend not to be super common naturally on the surface of the Earth. You can find them in nature, but they actually comprise around 70% of the mantle of the Earth. So around 70% of the mantle of the Earth is a perovskite phase. It tends to be a calcium iron silicate. So it's incredibly important geologically, but it's also important technically. And so what I'm going to do is I'm going to talk about perovskites that I synthesize, and I'll talk about some really, really interesting subtle structures that really you couldn't understand fully until probably the last, let's just say 15, 20 years as new technology and new instruments have allowed us to take a look at things at an atomic scale. So what I'm going to do is I'm going to give you a brief introduction to perovskites and their uses. I'll tell you a little bit about why I'm interested in them. And then what I'm going to do is I'm going to talk about the effects of temperature and divalent cation substitutions on one particular kind of perovskite. I'm going to focus on lanthanum ferrite, and I'll tell you why that's important in just a minute, okay? So what I'm going to do is add divalent cations, and today I'm going to focus mostly on calcium. So what happens when you add calcium to lanthanum ferrite and change the chemistry? And so what we're going to do is we're going to look at what happens compositionally as you add calcium, and then we're going to look at what happens in terms of what happens when you increase the temperature. So we'll work across this phase diagram in terms of composition and temperature and use different techniques to construct the phase diagram together. Okay? And then I'm going to talk a little bit about one of the interesting intermediate phases called the Grignard phase. There hasn't been a lot of work done on the Grignard phase, it's a very interesting intermediate phase, and a lot of times I think people, when they identify this phase in nature and you do X-ray diffraction on it, it looks very much like a perovskite, has the same stoichiometry as a perovskite almost, but it's not a perovskite. And it turns out that it has some really, really interesting properties that I think there could be some applications for. So I'll introduce you to that today. And then if I have time, and I think I will, I'll talk a little bit about some magnetic behavior. And so these are just a few little pieces that allow us to construct what I'll call a pseudo-binary phase diagram. And I assume everybody in here kind of knows what a phase diagram is that correct? Okay, so we're going to construct a pseudo-binary phase diagram together. And the way I'm going to end the presentation is I'm going to show you the pseudo-binary diagram in the end. By the way, I do love questions, so I like to answer questions as I'm talking. So feel free to interrupt me anytime you want, okay? I'm willing to actually take questions now if you have any. Are there any questions right now? Okay, that's okay. All right, so perovskites. I'm guessing most of you know what a perovskite is. You probably learned a little bit about it. If you have an introduction to materials textbook, if you've taken material science, you've probably learned a bit about perovskites. They're a fairly common crystal structure. They have the composition AbO3, cation A, cation B, and 3 oxygens. I am interested in them primarily because they're mixed ionic electronic conductors. In other words, in many cases, these materials will, at the right temperature, will conduct both electric current and ionic current. And that means you can use these materials for things like fuel cells, you can use them as sensors for gases, you can also use them to separate gases. So you can, for example, separate oxygen from air. And so that's the primary reason I've been interested in them historically. But there's other applications as well.
They can behave as superconductors in some cases, high temperature superconductors. Low temperature superconductors, my bad. They also can be semiconductors or insulators, and they have a variety of potential applications. They can be used in electronics as sensors, dielectrics. They can be magnetostrictive, they're pyroelectric, piezoelectric, optoelectric. They can be used in photovoltaics. There's a lot of work going on right now to use them in solar energy. They can be used as catalysts. They're primarily used as catalysts for volatile organic compounds. And their ionic conduction properties make them useful for things like syngas production, fuel cells, oxygen sensors, and energy storage, as I said earlier. My primary interest in these materials has been because of their value in syngas production. And so I thought I would just talk about that just briefly. If you have natural gas, and let me back up a little bit. When you're drilling for oil in remote areas, for example, in the jungle of Africa, or in a far-off desert, or out in the ocean on an oil platform, or in our country in the far north region of Alaska, when you're drilling for oil, often at the same time, or I should say almost always at the same time, you're producing substantial amounts of natural gas. And what we do in those remote areas right now is we flare it. We flare the natural gas. In other words, a lot of the energy that we're harvesting or trying to harvest from the earth gets burned while we're harvesting it. We waste that energy, which is kind of a sin. It's not something we should be doing. So if you could take that natural gas and convert it into a liquid fuel, you can then add it back to the oil that you're pulling out of the ground and ship it. The reason we flare it is because it's too expensive to ship gas in a gaseous form. You can ship it in a liquid form over large distances, but not in a gaseous form. You might be able to ship it 100 miles or 100 kilometers, but you can't ship it for tens of thousands of miles, or for thousands of miles. So one technology that has a lot of potential to make syngas production very economical is membrane technology. And the way it works is that you have a membrane, and on one side, let's say you've got air, and this would likely be high pressure, preheated, spent air from some process. And then on the other side, you have natural gas. If you have air on one side of the membrane and natural gas on the other, the oxygen partial pressure difference is enormous. And what happens is you'll drive oxygen from one side of the membrane to the other. It's a very, very large PO2 gradient, orders of magnitude. And if you have an appropriate catalyst on the other side of this membrane, as the oxygen comes across, rather than reacting with the CH4 or CH3 or whatever is in your gas to form H2O and CO2, it will react to form hydrogen and carbon monoxide. So you have to have the right catalyst to make this happen. And if you make CO and hydrogen, that combination of gas is extremely valuable, because you can now take that gas through a process called the Fischer-Tropsch process, which is a process that requires you heat it up and run it through some pressure cycles in the presence of another catalyst. You can convert that into a liquid fuel. And so that's the idea. So you create these membranes that operate at relatively high temperatures in this fairly hostile environment, because it's reducing over here, oxidizing over here. So this material has to be stable, and ions have to be able to conduct through it, and it gets very warm. It's about 900 degrees C perhaps. So it has to be a very robust material. Down here, this is a picture of the United States at night from satellite. I don't know if you can all see it, but all these lights that you see are lights from cities, with the exception of, let me make sure I'm pointing in the right place. Yes, with the exception of this little area right here. Anybody know what state that is? It's North Dakota, very good. That's the state of North Dakota. And what you're seeing there is not light from a city, but you're seeing light from all the natural gas because of all the oil and drilling operations that are going on in North Dakota right now. And so we're wasting enormous amounts of energy, obviously about a city's worth of energy every day up here in North Dakota. And if we could convert that natural gas into liquid fuel, we could make a lot of money off it. And the amount of money you can make off of this membrane is in the tens of billions of dollars per year. So so if you can make this technology work, you can be very, very wealthy. You can also make syngas from coal operations and other operations as well. You don't have to just use natural gas. You can make syngas from coal. I won't go into this, but that's an important area, obviously, for China and for the United States too, of course. So what I'm going to do, this microphone is heavy. What I'm going to do is kind of start at the atomic level, and we're going to talk a lot now about perovskite structure and the stability of the perovskite structure and different crystal phases. And I'm going to focus, as I said, on the lanthanum iron oxide system. So I'm going to focus on this lanthanum oxide, iron oxide, calcium oxide phase diagram. And it turns out, my colleagues and I have a patent on this particular composition for syngas production. And it's right now the membrane that is still, I would say, one of the most favored membranes for producing syngas using this technology. The problem is that the membranes that we developed with somewhat of an empirical approach are in a region where we don't have a phase diagram. So what I'm going to do is try to understand what the phase diagram looks like as we go from this perovskite phase over here to the other side of the phase diagram. By the way, there's not a perovskite over here. On the other side of the phase diagram is this Ca2Fe2O5 compound. And it's called different things, but often it's called brown millerite. So this is a brown millerite structure, and this is a perovskite structure. And I'll show you what those structures look like in a little bit more detail here shortly. And so the question is, do we have a solution in effect all the way across the diagram? What happens in the middle? And also very interested in how do the properties change as you go across this sort of slice across the phase diagram, okay? And it turns out that it's not simple. This is actually kind of a complicated phase diagram, but it's a very, very interesting phase diagram. And in thinking about this phase diagram, you have to think a lot differently than you normally do. And I'll explain that in much more detail here soon. So this is a perovskite structure. And if you look at a typical textbook, you'll see the unit cell for a perovskite, which is right here. And the unit cell has two cations in it. The A site cation, in our case, the A site cations are going to be blue or green. And blue represents calcium, green represents lanthanum. The B site cations are on the corners of this little cube. And in our case, the B site cation is iron. And then the oxygen atoms are located on sort of in these positions, I'll just say. So a unit cell is kind of a messy way to represent the structures that I'm going to show you in a minute. And ceramic engineers, geologists like to represent crystal structures as polyhedra rather than as unit cells. Metallurgists tend to like unit cells a lot, but in ceramics we like to use polyhedra. And so these polyhedra represent the perovskite structure just as well as the unit cell does. In the case of the polyhedra, though, you'll notice that the oxygen atoms are located at the interstices, or the corners, I should say, not the interstices, at the corners of the octahedra. The iron atom is in the center, and then the cations, the A site and B site cations, tend to be on the interstices or in the center. And I'll show you another way to look at it here in the next slide. So again, here's this little comparison between the unit cell and the octahedra, but I can represent the perovskite structure using a diagram like this. So in this case, the A site cations, the The A-site cations for example, lanthanum, are located between the octahedra in the interstices. The B-site cations are located in the octahedra. And then in this case, the oxygen atoms I've removed entirely, and the oxygen atoms sit on the corners of the octahedra. Okay, so that's how you view a perovskite structure. So it's just a very simple way of viewing it. And but most perovskites are not cubic. The previous perovskite I showed you was cubic. Most perovskites have a slightly tilted structure, and the octahedra can tilt one way or the other. Okay, and so depending on which way the octahedra tilt, that will determine what the symmetry of the crystal structure is. So in this particular case, this is an example where the octahedra tilt. Oops, something just happened there. Okay, so this is an example where the octahedra tilt this one direction, then the other, and then the other. So the octahedra tilt in alternating directions. You can imagine that they could all also tilt in the same direction, right? This is actually the structure of lanthanum ferrite at room temperature, and because the octahedra are tilted, the symmetry is not cubic, instead it's orthorhombic. And if you're into symmetry operations, it's a PBNM symmetry, or point group, I should say. Okay. So again, this is how I'm going to represent the structure of perovskites, just for simplicity, and so hopefully we're all on the same page now. All right, so what I want to emphasize is that I'm going to show you some images of the perovskite structures that I fabricated in a minute. And your first inclination is to think that I used some really high-tech method for making them, or maybe I made them by some sort of a coating deposition method. But I just want you to understand that all the samples that I'm going to show you images of were made by conventional ceramic processing techniques or powder metallurgy techniques. So in other words, we simply use a mill. We mill powder or a mixture of powders. We use lanthanum oxide, calcium carbonate, and iron oxide, basically. We mix them together in the right stoichiometry. We heat them up, which is called calcination. We press them together, we sinter them. And so it's pure powder metallurgy in the simplest sense. Okay? And we just use a very conventional tube furnace or a box furnace in order to calcine and heat treat these materials. So very, very simple process, and yet you're going to see in a minute we get these incredible, beautiful microstructures that look like they're synthesized by some fancy coating technique like CVD or MOCVD. And we're basically going to make nanoscale laminar composites using this method. Okay, so as we go to construct a phase diagram, so I teach solid state thermodynamics and phase transformations and kinetics. And what I like to teach in my classes is the following concept, that proof of a mechanism, proof of a phase diagram, proof of a scientific concept, proof of a hypothesis is less, or is often, I should say, less like a mathematical proof than it is like a proof in a court of law. So in other words, in order to prove a phase diagram, you have to use many different techniques in order to gain a high level of confidence of what the phases are and where the phase boundaries are. And oftentimes, if you use one technique, you can fool yourself, and it might be 20 or 30 years later where someone like me comes along and proves you're wrong. Okay? And so it pays to use many, many different techniques to look at different things in different ways, just like it pays to surround yourself with people that have diverse ideas, right? I always like to surround myself with people who come from different disciplines, different backgrounds, different countries, because they have different ideas than me. And that's true in science as well. Never believe your first experiment. Always do more experiments in order to verify something. Okay? So proof of a mechanism is like a proof in a court of law. Proof of a phase diagram is like a proof in a court of law. So I'm going to use a few techniques, and I don't have all of them up here, but in the next X number of view graphs I show, I'm going to talk about high-resolution transmission electron microscopy. And actually, I'm going to talk specifically about Z-STEM. Z means atomic weight. And so it's ultra-high resolution scanning transmission electron microscopy, where you can also determine the atomic weight of the elements that you're looking at. Very important in the study that I'm about to do. And that particular technique is what's allowed us to really understand this particular phase diagram. It's critical to understanding the phase diagram. I'll also show you some more traditional thermogravimetric analysis and differential scanning calorimetry. So in other words, we put a specimen into a furnace, we heat it up, and we look at the heat release and the weight change in order to understand phase transformations. I'll also use X-ray diffraction and neutron diffraction, so diffraction techniques, and we'll do these experiments as a function of temperature in some cases. We'll also have some dilatometry data. Dilatometry means that you're measuring the thermal expansion of a material, and by measuring the thermal expansion of the material, when you see a change in the coefficient or you see a transient, that tells you that you have a phase transformation. And then we'll also use vibrating sample magnetometry, high temperature vibrating sample magnetometry, which allows us to look at the magnetic properties and look at magnetic phase transformations. So all of these things together allow us to paint a complete picture of the phase diagram, and different instruments allow us to look at different aspects of the phase diagram. So the first one I'm going to start with is X-ray diffraction, and I expect most of you are familiar with the technique of X-ray diffraction. You simply send some X-rays in sort of a collimated beam towards a sample, and you look at the diffracted X-rays and you look at the change in that diffraction pattern, and from that you can determine the crystal structure of a material fairly well. There are some issues with it, but it's a pretty good way to determine crystal structure. You can't always determine exactly where atoms are in the structure, but you can usually determine the crystal structure with some accuracy. So I'm going to do this first, and the first thing what we're going to do is we're going to look at what happens as a function of composition. What happens to lanthanum and ferrite as we add calcium? Very simple thing, okay? So, and I apologize, somehow the diffraction pattern got corrupted when I upgraded just before I left, but the basic information is here. So, so this is the intensity, peak intensity versus angle, and each of these peaks is associated with a diffracted plane of atoms. And I'm just going to focus on these peaks over here in just a second. But what I want to point out is each of these is a different X-ray diffraction pattern. This is pure lanthanum ferrite, 10, 20, 30% calcium, 40. This is 50% calcium. And we're going across that pseudo-binary phase diagram from the perovskite phase, lanthanum ferrite, over to the pure calcium iron oxide, which is called brown millerite, and finding out what happens along the way. And what you see in this data is that somewhere between 50 and 60%, you can see an obvious change in the peak intensity. And in fact, you've got this fairly intense sharp peak that then converts into what are two kind of small peaks, okay? So you might assume, and this is what was assumed in the literature for many years, that the solubility limit of calcium in lanthanum ferrite is 50%. Turns out that's wrong, and we figured out it was wrong pretty quickly, because even though we had these similar X-ray diffraction patterns, when you look at the microstructure, you can see evidence of second phase, and so that didn't make a whole lot of sense. And people in the literature had reported this and also seen a second phase, but never questioned it, because they believed their data. They believed one set of data, and again, proof of a mechanism is less like a mathematical proof than it is like a proof of important law. All right, so here's the thing. So if you look at these crystal structures, this is the orthorhombic perovskite that I talked about earlier. Okay, this is pure lanthanum ferrite. Over here, on the other side of this system, is the brown millerite. So the difference between the brown millerite and the perovskite is kind of simple in a sense. Remember, the green atoms represent lanthanum, and as you add or substitute calcium for lanthanum, because the calcium is divalent, lanthanum is trivalent, you end up having to create some oxygen vacancies. And so these oxygen vacancies are aligned in this brown-millerite structure. And what happens when you add calcium to lanthanum to the point where you get rid of all the lanthanum is that you create these vacancies that are all on the 100 plane, and because you've got a valence change, in order to compensate for that valence change, the iron also has to change valence, and so the octahedra collapse into tetrahedra. So the difference between the perovskite structure and the brown-millerite structure is that in the brown-millerite, you have octahedra, then tetrahedra, then octahedra, then tetrahedra, and so on, alternating layers with vacancies in between. Now, if you look at this brown-millerite, it's a pretty interesting structure. As you can imagine, because you've got oxygen vacancies, that creates channels that things can diffuse through, right? It also turns out this particular structure has a lot of very interesting catalytic properties. This material can be used as a catalyst. So brown-millerite is a really interesting material, but it's not very durable. It's not something that would operate in a syngas environment. The Grignard phase is something that we weren't sure that this Grignard phase existed in the middle of the phase diagram, but we speculated that it might. And so the Grignard phase is basically intermediate to the brown-millerite and the perovskite. In other words, we've removed a fraction of the lanthanum. So we have a layer of lanthanum, then calcium, then lanthanum, calcium, and so on. And so we have octahedra, tetrahedra, octahedra, octahedra, tetrahedra, octahedra, octahedra. So that's the structure of this Grignard phase that we were speculating might be out there in the middle of the phase diagram. So I want you to kind of remember this image right here, because I'm going to show this to you again here shortly. So it's these layers of octahedra with the lanthanum and the calcium. Now, to prove that this phase exists is very difficult by X-ray diffraction. As you can imagine, the diffraction patterns for all of these are kind of similar. What happens is the tetrahedra give you little extra spots, but to sort out the structure of these materials from one another using low resolution X-ray diffraction, for example, is very challenging. In order to sort these structures out, you have to do very, very careful Rietveld refinement, or maybe there's another technique you can use, and I'll show you that in a second. Okay, so knowing what these structures look like, you can actually simulate the X-ray diffraction patterns using various programs. We use a program called ZSAS, and you do Rietveld refinement essentially of the structure, and then you can reconstruct the X-ray diffraction pattern. And I'm showing you three patterns here. One, assuming that we have, so these are not real patterns, these are simulated. One, assuming that we have pure perovskite. One, assuming that we have Grignard phase, which is the red curve. And then one for brown-millerite. Now this scale is blown up dramatically. And there's a couple things I want you to note. One, make note of the fact that this is quantitative. This is a quantitative calculation. And you'll note that the perovskite peak is much, much larger than the Grignard and the brown-millerite peak, okay? And also you'll notice that these peaks are very, very close together, and they actually overlap with one another. So just imagine if you have a mixture of a lot of perovskite and a little bit of Grignard phase. This Grignard peak would get buried inside the perovskite. It's very difficult to identify and very difficult to separate these phases unless you do extremely careful X-ray diffraction measurements and extremely careful Rietveld refinement. But it turns out that we were able to do high-resolution X-ray diffraction and develop a high level of confidence that, in fact, we do have Grignard phase in this system. But we wanted to prove this to ourselves in another way. And that technique is Z-STEM, high-resolution TEM. So this is a very powerful microscope. You might have one here on campus, I would expect. This is a FEI unit called a Titan. This particular system also allowed us to look at the atomic weight of the elements. So here's a high-resolution TEM image of a specimen that we made, and this particular one is, let's see again, lanthanum 0.33, calcium 0.66, oxygen roughly 2.66. So this composition would be the stoichiometric Grignard phase, if we could make it perfectly. All right? So what you're seeing here is a high-resolution TEM image of our crystal structure, and you'll notice I superimposed that Grignard structure, that little cartoon that I showed you earlier, onto the diagram at the same scale. So you can see the little green atoms, and then you see the octahedra, then the blue atoms, and the tetrahedra. So these bright spots are the lanthanum atoms because it's a higher atomic weight atom. And then these lighter spots are the calcium atoms. The tetrahedra are, you can't really tell probably from where you're at, but they're not spherical, they're little oval shapes. And that's because the tetrahedra overlap like this. Okay, so you get one tetrahedra then the other, and that creates a little oval shape. And those represent the iron atoms that are in the tetrahedra. And then these spots, which are more spherical, represent the iron atoms, which are in the octahedra. The oxygen atoms are invisible. Okay? So this is actually the first high-resolution TEM image showing the Z contrast of the Grignard phase. Okay? And here's a lower magnification of that. So the one I just showed you was a very high magnification. I think the bar at the bottom was 1 nanometer. And here are two lower resolution or lower magnifications of that material. And you can see these beautiful, beautiful laminar structures. And if it's dark, that means it's rich in lanthanum. It's rich in calcium. If it's light, that means it's rich in lanthanum. So the perovskite is this lighter region here. And again, this one is lanthanum 0.4, calcium 0.6. Sorry, here we go. Lanthanum 0.4, calcium 0.6. So we're a little bit calcium rich in this case. So we're in a region where you'd expect to have perovskite plus brown millerite, perovskite plus Grignard phase, and maybe a little bit of brown millerite if you don't mix it right. So you'll see that. Sorry, this pointer's. So we have the Grignard phase, we have the perovskite phase, and in a few cases we have some brown millerite. And the brown millerite phase is there accidentally because this is a binary system, and so to have 3 phases in equilibrium at this composition would be a violation of Gibbs phase rule. And so we have this brown millerite phase here because we don't have perfect mixing. And this is a slightly intermediate magnification over here where you can see the perovskite phase and the Grignard phase fairly nicely. Okay? So these are very difficult images to get, as you can imagine. But they give us confidence that we have the Grignard phase. We've verified it now. We've seen the Grignard phase with our own eyes. We've seen the brown millerite phase with our own eyes. And we've seen the perovskite phase with our own eyes. And we know that all of those phases exist across the phase diagram. So using that information plus high-resolution X-ray diffraction, we're able to show that the solubility limit of calcium in our perovskite, our lanthanum ferrite, is about 38%. Okay, so we were able to prove within about 1% that the solubility limit is 38%. Between 38% and about 62%, we have a 2-phase region of perovskite plus Grignard phase, and then beyond that, we have a 2-phase region of Grignard phase plus brown millerite. So now we've gone across the diagram at room temperature, and we know what all the phases are in the phase diagram. Now the question is, what happens when you go up in temperature? So now what I'm going to do is look at the high temperature phase transformations. We're also going to look at the expansion behavior a little bit. We're going to use, first of all, calorimetry, and a little bit later I'll use some weight change measurements as well to look at what happens in this system. So this is a niche calorimetry system, and what we do is we put a specimen in this system and we'll heat it up either in air or under inert conditions or reducing conditions. And so here's some data. So this is calorimetry data, all right? And I'm showing you basically the heat that's generated, relatively speaking, versus temperature. So in other words, what we're doing is we're heating our specimen up and we're looking for phase transformations. So as I heat this material up, when I see a peak, that means that there's a phase transformation. Heat has been absorbed in this particular case. So this is 0% calcium, 10, 20, 30, and 40% calcium. Okay, so as I heat this material up in air or in an inert atmosphere, and by inert what I mean is we have about 5 parts per million oxygen in it. So as we heat this material up, we see a peak. For the 0% material, it's right around 1,000 degrees. And as you add calcium, that peak becomes lower and lower. So in other words, because we've added a divalent cation, we've changed the valence of the iron, we put vacancies in the material, it's easier to get that phase transformation to take place. The question is, what is that phase transformation? Right? Well, using high-resolution, high-temperature X-ray diffraction, we can determine what the phases are. And so this is showing 2 examples for calcium for the pure lanthanum ferrite with 0% calcium. And then the second example has 30% calcium in it. And so as we heat up this pure lanthanum ferrite, right around 1,000 degrees C, we see a transition from these sharp peaks to these 2 smaller, less intense peaks. And to make a long story short, you have to do a lot of work to do the characterization. To make a long story short, we're going from the orthorhombic perovskite to a monoclinic phase, monoclinic perovskite. In other words, all the octahedra have tilted the same way. So in this particular case, all the octahedra alternate, right? And in this case, the octahedra all tilted the same way, which makes it a monoclinic structure. Okay? And as you heat the material up even further, what happens is that monoclinic structure ends up doing this, and eventually the material becomes cubic. Okay? As you heat it up, it becomes more and more symmetric. And that's true for both of these systems, except that in the 30%, obviously, the transition is lower. So using a combination of dilatometry and X-ray diffraction, or not dilatometry, calorimetry and X-ray diffraction. We've also used dilatometry for this purpose too. We can actually see the phase transformations from the peak in the calorimetry data, but also from the change in the thermal expansion behavior. And this is showing X-ray diffraction data as for the 0, 20, or 0, 10, 20, 30, and 40% calcium materials. And you can see that as we heat it up, it goes from orthorhombic perovskite to monoclinic. Here it goes from orthorhombic to monoclinic, orthorhombic to monoclinic, orthorhombic to monoclinic. And here it goes from orthorhombic to monoclinic to cubic in the 40% case. And you can see that in each case, as we add calcium, this transition temperature goes to a lower and lower temperature. Okay, so this gives us another piece of the phase diagram for what happens over on the lanthanum-rich side. Okay, we also want to know a little bit about the calcium-rich side of the phase diagram too. So what I want to do now is move across the diagram to this Grignard phase. This Grignard phase is quite interesting. What I want to do is just take a minute to talk about a really special kind of property of the Grignard phase that most people aren't aware of, and I think could have some really important applications in for example, space, in oxygen separation, in membrane technology, and in gas absorption technologies. And nobody has tried to use the Grignard phase, as far as I can tell, for any commercial applications yet. But I believe there's quite a few applications out there for this particular material. I use neutrons a lot to characterize materials. I do neutron diffraction. And usually you use neutrons because unlike X-ray diffraction, neutrons can tell you exactly where an atom is, or more precisely where an atom is in a structure. Neutrons are also really good for penetrating materials. So you can look at residual stress, and you can look at the inside of materials. But in this particular case, I used neutron diffraction for all the wrong reasons. And the reason I used it wasn't because of those advantages. I used it because we had a furnace that was on a neutron diffractometer that allowed me to go to higher temperatures than I could go to with my X-ray diffraction system. So if I could go to 1400 degrees C in my X-ray diffractometer, I would have done that. So sometimes you don't use the tool for the right reason, but you use it because you don't have a better tool. And so that's why I did neutron diffraction. But the point of this is that one of the things that we found out is as you heat the Grignard phase up to a very high temperature, right around 1320 degrees C, the material goes from an orthorhombic structure to a very simple cubic structure. And in addition to going from an orthorhombic structure to a cubic structure, it goes through what's called an order-disorder transformation. In other words, at these temperatures down here, the lanthanum atoms and the calcium atoms are all on 101 planes. They're all ordered. But as you go above that 1320 degrees C, and it becomes cubic, the lanthanum and the calcium don't care where they are so much. So the lanthanum and calcium become randomly distributed in the structure, as opposed to having an ordered structure. So that gives it some pretty interesting properties. So this is kind of a really, really bad diagram. This is the kind of diagram I always tell my students never to show, okay? But bear with me, okay? So in this diagram, there are three things to pay attention to. And I'm going to simplify this in a minute. The first thing is the red curve. And the red just represents a thermal cycle. So all I'm doing is I'm heating my material up, I'm cooling it down, I'm heating it up, cooling it down, I'm taking it through a cycle. And this looks like kind of a weird arbitrary cycle, but there's a very specific reason that I use this cycle for this particular illustration. And then the blue is the calorimetry data, and the buttons are so close together I can't hit them. So the blue is the calorimetry data. And the thing that is important to pay attention to here is this one peak. So that one peak is at this temperature, which is around 1320 degrees C. And so that is the order-disorder transformation. So we actually see the order-disorder transformation in the calorimetry data, okay? And then this green data, which I haven't shown you any of yet, the green data is weight change data, okay? So as we heat this material up and we go through these different cycles, we measure the heat release and we also measure the weight change. So what I'm going to do now is I'm going to get rid of this temperature cycle, and I'm going to get rid of this blue curve. We're just going to focus on this green curve. All right, so this is the green curve only. Okay, so bear with me. So here we go. So this is our starting weight right here. Okay, so we're measuring the weight change as a function of temperature. And so as I heat this material up, in this particular case, I'm heating it to 1100 degrees C, so that says 1100. So I heat it up to 1100 degrees C, and my material loses a little bit of weight. The reason it loses weight is because of entropy. As you heat a material up, you create more oxygen vacancies, and you therefore lose weight, okay? So as I cool it back down, in this case I go back down to 700 degrees C. And when I go back down to 700, I gain weight. I come back to almost where I was, but not quite. So in other words, I pick up oxygen out of the atmosphere, okay? If I take this material then and heat it up to 1400 degrees C, so I've taken it above the order-disorder transformation, okay? So now I've got the cubic structure, it's a disordered structure, and you can see, again, I've lost quite a bit of weight. But now I cool it down, and what happens when I cool it is it gains a whole bunch of weight, picks up a bunch of oxygen. When I cool it to 700, instead of coming to here, I go to here. I cool it to 600, 500, then I go to 200 degrees C. And so I'm gaining massive amounts of weight because the Grignard phase, this disordered Grignard phase, this disordered structure can absorb lots and lots of oxygen, just like a sponge, okay? Now if I take that material and I heat it up, back up to 1100 degrees C, okay? This is kind of an intermediate temperature, but I only hold it there for just a second. And I cool it back down to 700. You can see that I don't go back to this point right here. I go to a lower point. In other words, I still gain a lot of weight, but not quite as much. And I don't go back to where I was in the beginning. So in other words, if I heat treat it at 1100 for just a little bit of time, my sample has started to reorder itself. It's started to become more ordered, but it's not completely ordered. And as a consequence, I can't absorb quite as much oxygen. If I take that sample and I heat it up to 1400 degrees, or no, excuse me, back up to 1100 degrees C, but this time I hold it for a long time. You can see a little bit of weight loss here also. And then I cool it back down to 700. Lo and behold, I come back to exactly where I was in the beginning. So this Grignard phase can be used as an oxygen pump. So I can absorb oxygen from the atmosphere, I can give it up, I can move back and forth, I can cycle it, and I can do this over many, many cycles, okay? So it's got some really interesting properties. I can see it being used in all kinds of space applications, in sensor applications. It also has some really interesting properties, I think, for membranes too. And likely, it's probably a good catalyst. So why does it do that? Why does the Grignard phase pick up oxygen? So the phase was named after an individual, not surprisingly, named Grignard. And this is an image that Grignard collected in 1983 using one of the best microscopes of that era, which you can see the atoms in this microscope. And you can also, if you look very closely, it's a little hard to see in this room, but there are domain boundaries. So these are little nanograins, and they have an orientation, and they have these what we call domain boundaries. To the left is our work, and these two images are almost identical. In other words, the microstructure that we produced is almost exactly the same as the microstructure that Grignard produced back in 1983. Grignard theorized that the oxygen that was picked up when you cool it down got preferentially absorbed into these domain boundaries. And so we wanted to verify whether or not that is true. And again, we go back to high resolution TEM in order to try to prove this. Okay? So this is, these are two high resolution Z-stem images of the same composition. So this is lanthanum 0.33, calcium 0.6, iron 0.03 roughly. This is the Grignard phase. This is the ordered structure that I showed you earlier, and this is the disordered structure. Okay, see no Z contrast here, or very little. Okay? So again, this is the ordered Grignard phase, the low temperature phase, and this is what happens if we heat it up above 1320 degrees C and quench it to room temperature. Okay? So they look quite different. So why does this structure absorb oxygen from the environment? Is it because it absorbs it on these domain boundaries, or could it be that the oxygen actually gets picked up within the structure itself, within the microstructure? Well, there was a lot of work that we did in this, and I'm only going to just touch on it, and I'll just give you a little bit of highlight. One of the things that we did was you can't really do diffraction on typical electron diffraction on a region like this because it's too small to get a diffraction pattern, okay, from traditional TEM work. But what you can do is you can get a high resolution image like this, and from fast Fourier transform techniques, you can take an image like this and create a diffraction pattern. Okay, so this is not a traditional diffraction pattern that you would get within a TEM. What this is a diffraction pattern that is mathematically generated from the spots that you see in a high resolution TEM image. And what we discovered is, and then the other thing you can do, I should say, you can also do a digital analysis of regions like this and determine if they're richer in calcium or richer in lanthanum based on the intensities of the spots. And this area right here is about 20% richer in lanthanum than this region right here, based on the intensity of the points. So if we then do fast Fourier transform on each of these regions, we get a diffraction pattern. And what you discover is that the regions that are rich in lanthanum give you a cubic type pattern, as you'd expect. And the regions that are richer in calcium tend to give you also this cubic pattern, but you also get these extra satellite points that are associated with tetragonal symmetry. Okay, the tetragonal symmetry tells you that there are oxygen vacancies there. The cubic symmetry tells you that it's rich in oxygen. So what we're able to prove with high resolution TEM is that not only it is still possible that the oxygen is going into the domain boundaries, but the oxygen is also getting absorbed into the Grignard structure, which is probably one of the reasons why the kinetics of moving the oxygen in and out of this particular structure are limited, slow, relatively slow. Okay, so I'm going to talk about one final transformation, and then I'll show you the phase diagram, and then I'll let you guys ask questions if you'd like. So the last kind of interesting phase transformation I'm going to talk about today is a magnetic phase transformation. So these materials exhibit some magnetic behavior. They're soft magnets, and that magnetism can be observed using magnetic techniques, but it can also be observed in the thermal expansion behavior. So I'm going to just start by using the classic technique, which is vibrating sample magnetometry. And we're doing some high temperature vibrating sample magnetometry work. And so in this particular case, I've got, I'm just going to focus on material that's doped with 10% divalent cations. So we've got our pure lanthanum ferrite. We've got a material that's doped with 10% calcium. And just because it's interesting and for comparison, we've got a material that's doped with 10% strontium, and then one that's doped with 10% barium. So we have calcium ferrite, lanthanum calcium ferrite, lanthanum strontium ferrite, and lanthanum barium ferrite. And what we discover is that the material that's doped with calcium behaves very differently than pure lanthanum ferrite, and the materials that are doped with strontium and barium behave almost exactly like the lanthanum ferrite, which is very, very strange, to put it mildly. So when I saw this, I was very confused, and because when you add, this is called the Neal temperature. So we're going from this is an antiferromagnetic to paramagnetic phase transformation. And if you add a divalent cation, and you form, what's going to happen is you're going to form tetravalent iron. When you form tetravalent iron, what that's going to do is that's going to shift the phase transformation to lower temperatures. It's going to make it easier to make that phase transformation occur. Okay? So if you add 10%, I'm sorry, if you add 10% calcium, 10% strontium, 10% barium, because of the change in the iron valence, would all be the same in each case, or you'd expect it to be, very likely would be, you'd expect all three materials to have similar magnetic properties. That is, they would affect the phase transformation in the same way. Okay, so why is it that these divalent cation substitutions are not all equal, so to speak? So when you think about it, this took a little while to think about. When you think about this phase transformation, the antiferromagnetic to paramagnetic phase transformation in these materials has to occur because of what's called a superexchange interaction associated with the canting of the iron and oxygen atoms. So this canting influences the antiferromagnetic behavior. So as you can imagine, antiferromagnetic behavior means that you've got these opposite spins in the iron atoms, and these spins couple across the oxygen. And so if the atoms are associated with one another through this this oxygen atom, in other words, this angle, this canting, as you change that angle, you're going to change the antiferromagnetic behavior, or at least change the nature of when that phase transformation can take place. So that angle, it's intuitive anyway, must have something to do with the phase transformation, right? So, and so this is showing the fact that, you know, the calcium and lanthanum atoms are almost the same size, okay? And the barium and the strontium atoms are much larger. So your immediate thought would be, you know, as you add calcium to lanthanum oxide, you'd see very little change in the lattice parameters. And as you add strontium and barium, you'd increase the lattice parameter. But of course, it's more complicated than that. Because as you add these divalent cations, you change the iron valence and you also put in some oxygen vacancies. And so in reality, what happens, because of the change in the valence, is that as you add calcium to the lanthanum ferrite structure, you reduce the lattice parameter considerably. And then as you add strontium or barium, the lattice parameter comes back. It is almost, you know, it's comparable to where it was in the case of the pure lanthanum ferrite. Okay, so clearly, it's a complicated system. So here's another piece of data. This is thermal expansion data. And so you can also see this phase transformation and thermal expansion data. So one of the things I wanted to do is verify that, you know, our magnetometry data was correct. And so we also do dilatometry. In other words, we measure the length of our specimen as a function of temperature. So if you take the derivative of the thermal expansion data, you can see these phase transformations pretty nicely. So this is our lanthanum ferrite, our lanthanum calcium ferrite, our lanthanum strontium ferrite, and our lanthanum barium ferrite. And again, using thermal expansion, we measure a transition of 457 in the pure material, and we see a reduction of about 100 degrees in the calcium-doped material. And then in the strontium-doped and barium-doped materials, we come back to almost where we were in the pure materials. So we got these two sets of data that corroborate one another and verify that indeed the magnetic phase transformation does occur as we measure by magnetometry. So here's a summary of our data, and also I threw in some data from some other research groups. So this is what's called the Néel temperature of the phase transformation for the pure material. This is for the calcium-doped material. There's a bit of scatter here, but this is for the strontium-doped material, and then this is for the barium-doped material. And these are our studies in black compared to some studies in the literature. Okay, so why? Well, again, I love neutron diffraction. So now I'm using neutron diffraction for the right reasons. So what we decided to do is go back and look at our structures. It's really difficult to measure bond angles by X-ray diffraction, but neutrons allow you to measure bond angles quite accurately because you can determine the relative positions of atoms really accurately. It's a little bit tricky in this system because when you have magnetic behavior, it's difficult to take into account when you're using neutrons. But we were able to do some very careful field refinement and measure this bond angle, measure this angle between our iron, our oxygen, and our iron. And that angle right there, we believed, was associated with the change in the odd change in magnetic behavior. So if you look at the data, you can see that pure lanthanum ferrite has an angle of 156 degrees roughly from here to here to here. So that's 156. In the calcium-doped material, it's exactly the same. Turns out it's exactly the same. So the change in magnetic behavior associated with calcium doping must be associated with the change in the iron valence to tetravalent iron. You'll notice that the strontium and the barium materials have a much higher bond angle. In other words, adding those materials increase the bond angle by about 5 degrees. And it turns out that there's another very good group that did some research, Zhu and co-workers in PhysRev, and published a really nice paper where they did a systematic study on some materials as a function of that bond angle, that canting of cation through the oxygen atom. And they were able to prove that for every 4.5 degree increase in the bond angle, you get a 50-degree increase in the anneal temperature. So the odd behavior of the strontium and barium is due to the combined effect of the change in valence of the iron and the increase in the bond angle, which kind of explains the unusual behavior. Okay. All right, so last slide. So this is a summary of everything that I just said. And so this is the culmination of a lot of work, as you can tell, in order to construct a phase diagram. If you've ever worked on a phase diagram and tried to do all the experimental work to construct one, it's a lot of work. I've worked on a number of phase diagrams. It usually takes me doing experimental work. It takes me, I would say, 1 to maybe 3 or 4 years to construct a phase diagram. So it's a very long process, takes a lot of effort and a lot of thought, and you want to be very efficient in terms of the selection of the experimental technique that you use. So this is temperature on this axis, and this is calcium content down here. So we're going from pure lanthanum ferrite over here on the left to the pure calcium ferrite over here. So this is perovskite, this is brown millerite. And as we go across the phase diagram at low temperatures, we have the orthorhombic perovskite up to this point right here. And at this point, this is where we start to form the Grignard phase. Solubility limit is about 38% calcium. And now we have this two-phase region of perovskite plus Grignard phase in here. This is the Grignard phase, which is a line compound, presumably. And then on the other side of this line compound, we have the two-phase region of the Grignard phase plus brown millerite. Now, if we focus on this lanthanum-rich side of the phase diagram, we have our magnetic phase transformation in here. As we heat it up, you'll remember that we had a orthorhombic to rhombohedral phase transformation, and that transformation decreased in temperature as we added calcium. So this is the temperature where we go from an orthorhombic structure to a rhombohedral structure. And if you get up to very high temperatures, you'll start to form a cubic structure. I didn't talk about that very much. In this region right here, we have our perovskite and Grignard phase, and then here we have our rhombohedral perovskite and Grignard phase. And then remember, the Grignard phase goes through an order-disorder transformation, which occurs up here right around 1320 degrees C. And then over on this side, and I didn't go into the details on this side, but we have a Grignard phase plus brown millerite, which transforms to a Grignard phase plus brown millerite with a different crystal symmetry. So that is the phase diagram. That's how you construct a binary phase diagram. So these are the conclusions, and I think I'm not going to read these because they're not very exciting, and I've kind of already mentioned all of it. So what I think I'll do instead is just end with this picture. Again, this is a presentation from the University of Utah, in the state of Utah. Our college has faculty in approximately 6 buildings, and most of our research and our faculty are in 2 buildings. This is showing one of our newer buildings called the Sutton Building, and my office is actually right in here. That's my office. The building is actually a museum and a teaching tool. It's full of fossils and rocks and minerals, and it's quite beautiful. And I would just like to invite all of you to come and visit someday. And if you come and visit, we'll find someone to teach you to ski or to fly fish